Okay, all right. So am I live now? Okay, so good afternoon, everyone. So we can directly start with the questions first of students who are present in the live session. So if you have any questions, you may please start asking. Later on, I will address if anything has to be addressed from the Google Sheet. Yeah,
Good evening,
I see a
ma'am.
message. Somebody is having a... Yeah, please go ahead. Yeah, please, first of all, please, I mean, if you can please turn on your camera, that will be better.
Okay, ma'am. Good evening, ma'am.
Good evening.
Myself, Professor Divesh, Assistant Professor in Government Engineering College in Gujarat. Ma'am, in assignment 1, there was a question regarding the what will be the voltage across the switch while it is in the turn off condition. So I have calculated the answer considering the ripple also. So as per my understanding, the voltage across switch will be equal to the peak voltage of the input as well as peak voltage of the output at the same, if both are at peak at the same time. So input voltage is 100, output voltage is 50, but that is average voltage. So the total voltage appear across the switch, that will be 150 definitely. But in that case, ripple was not considered. There was a 1 volt ripple also there in the output. So the voltage across the switch may be equal to 151 volts. Is it right, ma'am?
Yes, you can take into account the ripple voltage, but it will be half of that.
But 2 volt is there, so I have considered 1 volt.
Yes, that is okay. You can
but
take
ma'am, in assignment, it is wrong that told by that person, means the course supporter.
Okay, you write an email and I'll inform the concerned TA who handled that assignment that if someone has answered that. So you specifically email because not everyone has answered accordingly. So we will see if we can accommodate that. Okay.
Okay, ma'am. Okay. And second thing is that when we design any snubber circuit, so in that case, the losses has to be considered. So I have derived the answers from the equation that given in the lecture. In that case, I got that the small snubber having a minimum.
Repeat it? You are asking from where? Which part?
Gujarat, ma'am.
No.
I'm assistant professor in government engineering.
The course you are asking the question. I could not relate
snubber design.
Snubber design. Okay, snubber design. Yeah, what is the question?
Question is that is in increasing order of losses. No snubber, small snubber, and normal snubber.
See, that question, I know that I think you had sent an email, right? And
yes.
So that is the assignment. I don't want to disclose any answers beforehand. It was week 5, I think, in which the snubbers were there.
Yes, ma'am.
Hello?
Ma'am. Yes, ma'am.
Yeah, so I don't know right now whether it's already time, but I can give you the hint to look into it. You look into the graphs that is given, and also the turn off switching characteristics diagrams, those are given. And it doesn't compare large snubber, small snubber, and your normal snubber. It is comparing no snubber, small snubber, and normal snubber. I think you are confused the way that, I mean, it was brought to me by the TA. Appearingly, you have a confusion with, you're mistaken with large snubber. Large snubber is not asked in the question. So I would suggest you go back and look into it where the graph is also plotted, and that is specifically to the switching loss and not to the snubber loss or the total loss. So no snubber is not plotted in the graph, but it is given where I'm discussing about the switching waveforms, that how your turn off and turn on takes place. It's basically a turn off snubber. So turn off, how the voltage waveform changes and current waveform changes for no snubber, small snubber, and normal snubber. Skip the large snubber because that question is not dealing with large snubber. And in the graph, large snubber, small snubber, and normal snubber is shown. This no snubber part is not covered in the graphical representation where the losses are plotted with respect to the size of the snubber.
Ma'am, actually, the answer I have derived from the equation that which was given in the lecture. I think when we are not providing any snubber, then the losses is equal to EL IL TS by 2, I think.
That's what I told you. Your confusion is you are using equations which are related to small snubber, normal snubber, and large snubber, related to the snubber part, and not comparing it when no snubber is there. No snubber is equations cannot be used where snubber equations are derived. So equations itself change when you do not have a snubber.
Okay, ma'am, got it. Next question is that when we find dV by dt average divided by EW0 in the snubber design.
Okay.
So in that case, which value of E should be considered peak value or average value of voltage?
Peak value has to be considered.
Okay, ma'am. Thank you.
Well, see, one more thing I would like to tell you is that you are asking, I think, questions only based on assignments. And so I'm giving answers in general. I'm not answering here related to how specifically the assignment question has to be solved. That specific solution will be given to you anyway by the time the assignment submission deadline gets over. So you please look into it, and there specific, if you have a question, you can email to the team. But in general, when you are designing it, you should consider peak values.
Okay. Ma'am, one common request is that, ma'am, in an assignment or in an examination, when we have to give the answer in words, so we are making mistakes in that. For an example, one question was asked related to the ferrite core. So in the question, it was written that E ferrite core is considered, and you have to find the which ferrite core you have to use. So in my case, I have given answer 75. Why? Because E is already written in the question. So I got my answer was considered as wrong. Why? Because I have not written E75. So that kind of mistakes we are making.
No, that you have to be, I mean, specific about it, because those are the constraints in objective question paper. Because just 75 is not the name of a code. E75 is the name of the code. So that you have to be careful. I mean, that's what we can do. It's all limitations of objective exams.
So that kind of mistake we are making.
No, definitely during the exam, later on some visual checking is there. And if something very close is there, then definitely marks are given for that. And for assignments, specifically, if you're getting anything like that, you can, of course, email the TA and the TA will address it.
Okay. Ma'am, another question is like that, what is the unit of insertion losses? So person can write decibels, dB, decibel in bracket dB. So right now I am also confused what to write over there. So my answer get correct. So that.
See, you are not supposed to ask me answers of assignment questions in the live session. Okay, that limitation you should understand. I am not supposed to answer all that over here. Then
Okay,
if I
ma'am.
disclose all the answers, then what? So many students will get it. And then what is the objective of the assignment? You look into the video properly, thoroughly, you watch it, you will get all the answers. All answers are already present in the recordings, I mean in the lectures.
Okay.
Hello, good afternoon, madam. Thank you for giving your valuable time, ma'am.
Yeah, please go ahead with your question. Plus, please introduce yourself.
Yes, ma'am. Ma'am, myself, Muhammad Zakir, and I'm working professionally in automotive industry, and I have 10 years of experience in automotive component design. I have joined this course out of my curiosity in electrical circuits and power electronics. So basically, I'm from mechanical design background, CAD CAM. So, ma'am, my interest in electronics component, and ma'am, my question is from you that I have left my studies 10 years ago. So now I want to write a research paper. So how to proceed my topic is in mechatronics in seating system. So how to go ahead in this particular topic or field, ma'am?
No, actually, I can't help you with mechatronics. If you're very doing in power electronics,
Electronics, ma'am.
I
How
can
to
explain.
actually? Yes, ma'am. Yes, ma'am. Power electronics. How to proceed with the research paper? So, ma'am, actually, I'm not in touch of any faculty or right now. 10 years ago, I have left my study, so I want to pursue my hobby. So I want to write a research paper, ma'am. So how to proceed in that?
See, if you want to write a research paper, so then power electronics itself is a very big area. So you have to first pick up a research problem on which you are interested in. And then based on that research problem, you search extensively. First, do a proper literature review and understand what are the works that have happened in that particular research problem, what solutions that exist. And then further, you have to see what are the shortcomings in the solutions that are present in existing literature. And based on it, then if you can come up with a different solution, which is better than what is existing, and you have to then present the theoretical analysis, simulation verification, and if possible, experimental verifications also, then you can write a research paper.
Okay, ma'am. Ma'am, I don't have any for example, if I want to test any component for thermal testing, for EMI, EMC testing, so in that case, can IIT Guwahati help me in that if I have any problem or if I want to test any model or something?
See, what kind of help are you looking for? I mean, you are in which in
Ma'am, actually, if you- actually, suppose if I select any problem, for example, I have to test any product or test. So in that case, this is my.
I see there are, I mean, ways of helping to industries is like the industry, they do approach us and then projects are written and then accordingly the grants are decided based on which the research problem is investigated together by industry and IIT Guwahati. So that way it has to be approached via the industry to the concerned sections of IIT Guwahati. So that is the way industries are helped by IIT Guwahati.
Okay, ma'am.
Okay, so whatever is your specific research problem, you can like write a draft of it, like sort of a project proposal, and then you can approach here the industrial interaction sections, and you can of course keep me in CC as well with that. And then it's an entire project proposal where what is the funds that is required to do the research, all that has to, the industry has to provide to IIT Guwahati, and then collaborative research work is possible. Okay, ma'am. Okay. Just I want actually I wanted just my mother first target is to write a research paper, so I want to start with that. Yes. So then if you just want to write a research paper on your own, what I answered before, suggested before, that way you can go. It's better you do thorough literature review first. That will, you have to at the first place know what all research has happened in that area. Then only you can come up with anything different from that. So then after that, if you come up with a different idea, you can accordingly start. The next thing will be to verify those things by different methods. Okay, ma'am. Okay. Okay, ma'am. Thank you. Thank you, ma'am.
Hello, ma'am. Ma'am, I have one more question. Ma'am, whenever we design,
please turn on your video.
Whenever we find a value of inductor in
no, who is asking converter, the question?
For example, suppose we are finding a ripple inductor for ripple, L ripple. So in that case, we are considering a peak current.
No, actually, I'm not getting who is asking the question. Can you please turn on your video?
Ma'am, Divyesh.
Oh, yeah. Okay. Okay. Yeah. Please go ahead.
Ma'am, whenever we find a L ripple value for the buck converter or any converter, in that case, we are using peak value of current. But ma'am, if it is specifically asked, consider entire load range, then what to interpret about that? In that case, which current we have to consider to find out L ripple?
No, your question I am not following. But you have to clarify the question.
Ma'am, suppose we want to find out L ripple value of L ripple. In that case, we are considering peak current to find out the value of L ripple. But in the question, if it is written, find out the L ripple for entire load range, then also we have to consider the peak value of current.
Now see, you have to understand the context in which your peak value is used. So the objective of finding out L ripple is that whatever, the inductance value you will get, that will be able to limit the value of the ripple to whatever is the given value for all the currents, any current that may be flowing till the maximum current. So obviously using that, right? And now let's say your current became 5 ampere. So anyway, the L ripple inductance value is sufficiently high because it is chosen based on the peak values. So it will be obviously able to limit at 5 amperes of current as well.
Yes.
So that's why peak value is chosen. It is chosen such that for the entire load range, it is satisfied. So if suppose you have a problem that, oh no, I want to find out for the whole load range, and in the load range, if the percentages vary, So then you find limits and you have to choose the value which is maximum out of all the values of L ripples that you have found out. That value will be suitable for the design.
Okay. So, ma'am, suppose the peak power value is 600 watt. Then from that I have to find out peak current, and from that I have to find out L triple.
Yes.
Am I right, ma'am?
Yeah, what you are telling now is okay. If you do use peak values, it is fine. But yeah, again, as I told you, I am answering general concepts. The solution depends on exactly what the problem is and what specifically is given and what is being asked to find out.
Actually, ma'am, my confusion was anti-load range word. That was my confusion. Actually, we have to average power and the peak power. This we know. But anti.
Yeah, I already answered that. You please think over it.
Okay. Okay. Thank you, ma'am. Thank you.
Okay, so yes, so I'll take on YouTube. Okay, inductor design. Somebody is asking how to design the inductor for PFC boost converter. I mean, the concept is same. Whatever inductor design concept is explained, it is the same concept you have to use that based on the value of the inductor, how much current it has to carry, and what is the temperature rise, how much losses you can allow. Based on it only inductor design has to be performed. Just because it is PFC boost, not much difference is going to occur, and you have to go by peak values and not by the the lower values, because PFC boost means your current is going to be changing. And unlike your steady state boost, where the boost converter, where your current values are within a particular range. And one more thing is, in case of this inductor design for PFC boost, one thing you should keep in mind, whatever you choose should be able to withstand the lower frequency as well. Because the PFC boost will have a 100 Hertz component as well as the higher switching frequency components. So the material should be able to withstand the low frequencies as well. Okay, so what specification should we look for? This I already answered. Now, okay, it is sinusoidal with high frequency ripple? It is not sinusoidal with high frequency ripple. It is sinusoidal with low frequency, the supply frequency. Inductor blocks AC. Then how it is used in transformers? This question is not clear to me for which converter specifically you are asking. If you can clarify the question, then it will be better. What's the safety factor that are considered during selection and design of snubber? What do you mean by safety factor that are considered during selection and design of snubber? So if you're, in general, if you're talking about safety factor, means that, snubber itself is done for protection, and that is mainly your over voltage protection is done via snubbers, so that the voltage does not go beyond a particular limit whenever the spikes occur. So turn off and turn, especially during turn off, there can be a huge transient and a huge spike might come. So to limit that, to limit the stress on the device, we use snubbers. And many times they also limit the dV by dt. That means the rate at which the voltage across the device can change. That also can be limited by the snubber. and plus your safe operating area, that if you go into it, that also safe operating area is affected. In what part of the safe operating area you will be operating the device, that also gets affected by snubber. So this question actually is answered in the lectures. I would suggest to you that you go back and look into that part where I am explaining what does a snubber do. So there all the points are given that what does a snubber do and how it helps, and from there you will understand that how snubbers are required for protection. They help in protection of the devices. So which method of inductor design to follow area product method or KG method, since both methods are popular? Yes, both the methods are popular, and there is no such answer as this is better or that is better. It's just like this. You design, you may design using any of the methods or both of the methods, and you are expected to get similar solutions. And depending on the particular application, you have to see whatever values you are getting, if that is more suitable or for you or not. So inductor design, whatever is discussed in the course, that is just to that's like the preliminary design which is done. So for you to get which core you should you have to use all the calculations will give you the idea how to design the inductor. Then what is done is you actually design it practically, and then you see what inductance values you're getting. Mostly you will be getting what theoretically you designed it for. After that, in a converter, what we do is that we test it in the actual converter, and we see the temperature rises. Now, these are the places where the problem might come, that the temperature rise might be more than what is expected. Okay, so at that time, it's like you have to redesign the inductor with a bigger core, and you have to again check and test whether it works practically or not. So it's an iterative process, inductor design, from the product design point of view. And theoretically, when we do it preliminarily to get an idea in the first place, what should be the core, what should be the number of windings, which winding to choose, that you can get by any of these methods, area product method or KG method. Okay, so how to choose the current density JM and magnetic flux density BM for the inductor design? Yeah, so that's a good question. Actually, this is based on experience. People do it. Most of the time, your BM value at the first place, you will be getting an idea based on how much currents you have to carry. And mostly, we will be seeing that previous inductors or transformers that they were designed, what specifications they were designed, and what were the values of current density and magnetic flux density that were chosen there. And based on it, then you choose for your specific design the value. And then again, as I said, you start with a value which you see from previous designs, existing designs. And then you do your design, you find out what should be the core that you choose, what should be the wire that you should be using, how many number of windings and all that. You design it, and then finally you test it. At the test stage, you get to know whether it really works or not. If it doesn't work, then as I said, it's an iterative procedure. You do some modifications in the values, some adjustment in the values, and again redesign it. So magnetic design is actually an iterative process. Okay, so next question is related to some approximation value. So this please email to the TA. And I think this was, but as per answer provided in course is range 16, 18. Yeah, so this I can't really answer it over here because I don't remember the question. You please email the TA and the TA will definitely respond to it. Can you give some general guidelines how to select the value of percentage ripple in inductor design and capacitor design? Okay, so about the ripple in inductor design and capacitor design. So for capacitor design, a ripple, you go to the data sheets of capacitors. So that's actually a part of the last week where capacitor data sheets are discussed. So there you will see that how much ripple that particular capacitor can withstand, a physical capacitor can withstand. You will get the value from there. And based on it, then we do the calculations and find out which capacitor, what should be the value of capacitance, which will be able to limit the capacitor ripple value or the voltage ripple value to that. And as far as your percentage ripple for inductor design is concerned, so the ripple in the voltage and the ripple in the current, they are associated with each other. So if you see, it's the current ripple which leads to the voltage ripple. It's difficult to explain it, just verbally. Please look into the waveforms that are given in module 1. The inductor current waveforms are given first, and then after that, the capacitor voltage ripple waveforms are drawn, and they follow from the ripples in the inductor current. So, when we design it, we go by the reverse method. We see whatever capacitor, physical capacitor that you may be choosing, what is the ripple it can withstand, and then based on it, you can decide some percentage. And then also via that, you can also get to see that, okay, this is the inductor current ripple that can be allowed. So next question is, I want to design high frequency inverter. Should I go with full bridge configuration or resonant converter configuration? And what could be the possible reason for that? Okay, so this is how do you choose? That depends on your application. If you choose resonant converters, then that is like if you want very high efficiency, then resonant converters are used because switching losses are very less in resonant converters. And if you want a rather simple control, then you can go for the regular edge bridge converters as well, but the losses will be more in that. So what is your application and what it can allow or withstand? Based on it, you have to choose. Next question is, if I design the inductor using powder cores, but permeability is changing with DC bias. Number of terms is still unknown, so how to design using powder cores? I'm not really getting the question. The question is not clear, so please clarify your question. Here, by high frequency, I mean in order of 10 to 20 megahertz. Okay, so if you're doing in 10 to 20 megahertz, then you have to really look into it because that's a very high frequency. And they are used, see by previous designs then whether they are using edge bridge or resonant converters. Because even if you use simple edge bridge, you will have to go for special devices, GAN-based devices. You might have to go for that. And you have to see the topology which you are using. Why in forward converter magnetizing current is positive, rising from 0 and ending to 0, while in converters such as full bridge isolated buck converter, the magnetizing current is negative. And okay, well, the question is not very complete, but still, I mean, based on my assumption, I'll answer it. So if you see the circuit of forward current, you will see that there is no path on the supply side for the current to reverse. Whereas the moment you have edge bridge, a negative current is allowed. There is a path for that. So that is the reason behind it. So if the current has to become negative, the circuit, the way the topology is, the way the MOSFETs or the diodes are connected, it should be such that a reverse current flow should be allowed. Then only current can become negative. Okay, how to design of inductor for three-phase Z source inverter? Well, again, as one of the previous questions was asked related to PFC boost, so the steps of inductor design are not different. They are same, but it is the question of what are the frequencies that are present in the waveform of which the inductor has to support. What is the current waveform and what are the frequencies that are present in it. So whatever material you choose should be able to I mean, withstand those frequencies. Shall we design power electronic converter in general by selecting the components as per your calculations? Well, the question is not complete. Please clarify more. Okay, powder core permeability is varying with the DC bias or magnetizing force. In PFC inductor, DC current is varying. The design becomes a problem since inductance will vary with DC operating point. Well, I don't know what you exactly mean by that. The usual design procedure is that you first decide the circuit parameters. So at that time, you decide what is the value of L that you require. And then once you have decided what is the value of L that you need, then you design the inductor. That means you choose the core and the windings, the wire, which you will be using for making that inductor. Is there any particular guide or reference book for high frequency inverter filter design that you would suggest to start from? Well, for the frequency range that you have mentioned in your previous post, for that I am not aware of any book. So you can look into it. And actually, the frequency range that you are talking about, most of the time, power electronics converters that are designed presently do not deal with this frequency range. So mostly about several hundred kilohertz to about 1 megahertz to 2 megahertz is the frequency range in which most of the power electronic converters operate. So when you are talking about 10 to 20 megahertz, I think it is not really a power electronics based application. You are maybe for some other application you need that. So that's a special thing which you have to look into it. A general comment will not be correct for this. how the switching frequency is selected for operation of converter. So switching frequency is selected for operation of converter based on the power range for which the converter has to be designed. If it is high power, very high power, I mean to say that in the level of megawatt, then the switching frequency is less, maximum about kilohertz, few kilohertz is what you can go up to. Whereas medium power, that means you're about 100 kilowatts, 50 kilowatts, like that, 200 kilowatt. There you can be using tens of 20s, 40s, 50s kilohertz, like that. And when it's a low power, then you can go up to kilohertz of switching frequency. And with the new devices coming in, wide bandgap devices, there you can even go up to about a megahertz for very low power. Yeah, so this is to replace RF amplifiers. So with power electronic devices, yeah, that is what I was guessing, and that's why I didn't want to make a general comment, because this is replacing RF amplifiers with power electronic devices. That's not a general application that power electronics converter designs deal with, so you have to look into it specifically. Okay, if I would like to design the customized power electronic converter, such as buck boost converter, which is used in EV charger, then how can I make it? Well, I am not really very clear about your question, but I am assuming that you're asking that you have an EV charger application for which you want to design a buck boost converter. So the steps are, it's like all the modules have to be covered in the design process. The first begins with module 1, where you have to first do the circuit analysis. You have to find out the power limits of your application, the current limits, the voltage limits, and all that. And based on it, then you decide the values of L, C, and the switch voltage and current ratings. So that you have to design. Then further, you go to module 3, and you can go to module 2, use module 2 concepts for selecting the device and all the devices specifications. So that is what was covered in the power semiconductor devices in module 2. How to select the device, read the data sheet. So module 2 concepts will be required. Then you can use module 3 concepts to choose the gate driver. And then you can use the concepts covered for snubber design in module 4 for your snubber designing. Then after that, you can use the thermal design module to choose your heat sink. And then you do the magnetic design using whatever is covered in the magnetic design module, module number 6. And module 7, EMI reduction, whatever methods are there, that will help you in designing the PCB layout. Yeah, and also take care to some extent the common mode and differential mode noise, and you can choose the EMI filters also need, although that is not really covered in great detail. It's not really within the scope of the course, but module 7 will help you in that in EMI reduction. And then module 8 actually tells you the hardware, for the hardware, what all things you choose, what are the different specifications of it, what are the different sections of the converter. So it's designing of the converter is what the whole course is all about. So each module actually answers one particular design part of the converter. Okay, next question is, can you please mention some resources for learning common mode issues and electromagnetics compatibility? Yeah, so for that, please go into the lectures and see at the bottom of the lecture, there are many references which are given. So those references are good to start with for learning about these. All right, so I think all the YouTube questions I have addressed. Now I'll go back to Teams and see if there are questions here. So one says, I have one doubt when we are going to design a novel boost converter, what are the parameters that we have to consider regarding research and how to proceed with the design? Okay, see, whatever your topology might be, ultimately it will be containing some devices like MOSFETs, IGBTs, or diodes, and it will be having some L and C. So designing the converter means you have to choose the specifications for these. So for that, what you have to do is you have to first analyze your topology and find out the voltage ratings and current ratings of each device, whether it is a transistor or a diode or a L or a C. And you have to see what are the frequencies they have to withstand or at which they operate. So based on it, you first decide the ratings or the specifications of your devices, semiconductor devices, and inductors and capacitors. That is how you proceed with the design for any converter. Okay. Next question is, I have designed and developed novel type of boost modified converter. The main advice I would give you is carefully select the value of inductance. Choose the correct MOSFET switch into the carefully analysis of for thermal analysis. The more theoretical simulation insights where you will produce, the more practical problem for your converter you will be able to solve. Okay, I think this is a suggestion. Oh, actually, I think this is someone is responding to that comment. Okay. All right. Any other questions here on Teams? If someone wants to ask directly to me instead of typing, they can do so. Okay, okay. Let me see the Google Sheet now. Okay, first question is 7805 IC is a voltage regulator and what is a buck converter? All right. Yeah, so 7805 is a linear regulator and a buck converter is not a linear regulator. It's a power electronic converter. So what I would suggest you is that you open any data sheet of 7805 and you see what is inside 7805. 7805, you will see that it is just a simple transistor and that transistor is operated in the linear region. You know that the transistor can be operated in an active region, cutoff region, and in saturation region. In power electronics, we operate transistors in saturation and cutoff. We never operate it in active region. whereas linear regulators, they operate in the active region. And they are very lossy. That's why in the active region, both voltages and currents are high across the transistor at the same time. So there are more number of losses that take place. So, 7805 just uses a simple transistor, one transistor, which is operating in the linear or the active region, whereas buck converter is the circuit which is one of the power electronic converters, and it uses the power electronics concept, that's operation of the devices in saturation and cutoff. You have taught this course very nicely. Thank you so much, ma'am. If possible, please bring more courses related to power electronics and NPTEL in future too. Okay, so good to know that you like the course, and more courses we will see in future. Week 5 assignment question number 8 on performing calculation with the data given in presentation as well as YouTube problem solving session. The answer I have obtained is one, but the correct answers. For these things, week 5, I don't know whether already assignment submission deadline is closed or not. So I do not wish to answer it now, but definitely you will be getting the solution. And please email to the TA, not the TA who is conducting your live session, because they are not directly associated with the course. They are just PMRF scholars who are assigned by NPTEL to help you with the help you with the course. That's all, general understanding. So I would suggest that please look into the videos again of the lectures, and if you have any specific question, ask the course TA and not the PMRFs. Week 5 assignment question number 12, temperature rise has been asked in the question as we employ a fan. Want to answer right now? Okay, week 7 question. Again, I think this somebody has already asked. Okay, week 2 I can discuss, because week 2 the deadline is over. MOSFET is a bidirectional current device, but voltage is unipolar. IGBT is not a bidirectional device unless an antiparallel diode externally connected to it. Yes, IGBT is not a bidirectional current device. That's correct. MOSFET is a bidirectional current device. And why is it so? That is because MOSFET has a parasitic diode, which is called as the body diode of the MOSFET. Please look into the lecture again. So the MOSFET part, I think where the very first video on MOSFETs, I'm explaining that MOSFET has got a parasitic diode, a body diode present in it, because of which in MOSFET currents can flow in both direction. And IGBTs, when we see the physics of IGBT, then there is no such parasitic diode present in IGBT. And so that's why we have to connect an antiparallel diode. Externally, an antiparallel diode has to be connected. Please let me know the different areas of research in the field of power, especially in the area of mathematical control and stability of power converters. Mathematical modeling, yeah, what you are telling, mathematical modeling, control and stability, that is actually required for every power electronic converter. So any power electronic topology you select to investigate, you have to do the 3 that you have mentioned. Okay, again, week 6 question, I do not want to discuss now. Put the device in increasing order of switching losses, the smallest number. Yeah, this I already answered. Okay, the next question also I have already answered. How the switching time of MOSFET would be calculated using data sheet? Yeah, so this actually switching time, you can see that there will be that delay time plus the rise time which will be written. So delay time plus rise time is your on time. And then again for turn off as well, there will be some your fall time plus delay time. So that gives you the off time. So if you see the data sheet, you will be able to find out that. Okay, any data sheet you open, so you please go to the my lecture where I'm explaining the data sheet and go to the part where I'm reading out the times that are given, the on off different times that are given in the data sheet of the MOSFET. There you will see I have clearly shown what all when you sum gives you on time and what all when you sum gives you off time. All right, so I think I have answered everything, all YouTube questions, as well as the Google Sheet questions, and also on Teams. And it's also 5:15 now. So, but if there's any more quick questions, I can take it up.
Yes, ma'am. I have one question. Can you please share your email ID so that if any query, I can send you the draft of research paper?
Okay, okay. I think my email ID is already given on PTL that web page.
Okay, ma'am. Okay.
Okay, it should be given. Because some students, they email me by using that only.
Okay, ma'am. Okay. Okay. Thank you.
Okay, so I think all questions are answered. Okay, so can we end the session then? Okay.
Okay, ma'am.
Okay.
Thank you, ma'am. Thank you
Thank
for
you.
your valuable time, ma'am.
Thank you.